Hello, my name is Artem and I'm the author of Parsec per Century. Have you ever wondered why do some objects float in the water while others sink? If you study physics, you have to know that. However, you might not know what would happen if a person standing in the boat threw a heavy rock overboard. Would the water level rise, fall, or stay the same once the rock is in the water? You can stop the video and think about it, but now I will show you the solution. First of all, let's draw a diagram. So, this is the boat in the water, and there is a person standing inside, and it holds the rock. And now, the same person in the same boat decides to throw this rock into the water. So the rock sinks. And as I already said, the question is, will the water level rise, fall, or stay unchanged? So let's look at the forces which act on this boat. The most obvious one is weight. So the weight of the boat, of the human inside and the rock. So let's say that M capital is the mass of the boat and the human, and M small is the mass of the rock. So the weight is the sum of m's times g. Let's write here. So M capital is mass of boat, and M small is mass of rock. However, it's not the only force which acts on the boat. There is also another force, the upthrust force, which is defined in the Archimedes Principle. So the Archimedes Principle states that the upward buoyant force, which is also called the upthrust force, acts on a body immersed in a fluid, whether fully or partially submerged. So this is our body, the boat, and it's submerged into the water, which is fluid. And this force is equal to the weight of the fluid that the body displaces and acts in the upwards direction. So we know that the upthrust force is equal to the weight of the water displaced by the boat. And the weight is equal to the mass of the water times g. And mass is the density of the water times volume of water displaced times g. And this is true because the formula for density is mass over volume. Therefore mass is density times volume. That's what we have here. And let's write also volume is mass over density. We'll use it later. So the upthrust force and the weight of the boat are the only forces which act on the boat. And we know that the boat is at rest, which means that it doesn't accelerate in any direction. And therefore we can say that the upthrust force is equal to the weight of the boat. But we also know that the upthrust force is equal to rho Vg. So we can equate these two parts. Now we can cross g's, and what we want to find is the volume of water displaced by the boat when the rock is inside. So volume is equal to the total mass over the density of the water. And this is the volume when the rock is inside. So let's say that this is the case when the rock is inside. And now we need to find the volume of water displaced when the rock is outside the boat. So this is the case when it's outside. And to do it, we need to consider the boat and the rock separately, since we cannot treat them as a single body. as we could here. So in case of the boat, it is still quite simple. So what are the forces acting on the boat with a human? So obviously it's weight, and the weight of the boat is capital M times G, and the upthrust force again. So the upthrust force is equal to mg, and we also know that it's equal to rho vg. So rho vg, and again cross g's, and we get that the volume of water displaced by the boat is equal to the mass of the boat over the density of water. The reason why the boat floats is because its density is less than the density of water, and in this case as well, the average density of rock, human and boat should be less than the density of water to make it floating. However, the density of rock is larger than the density of water, and we can also write it as density of rock equals K times density of water, where K is greater than 1. And we know that the rock sinks, therefore the volume of water displaced by the rock is equal to its own volume, and its own volume is equal to the mass of the rock over the density of the rock. And we know that the density of the rock is K times the density of the water. So this is the volume of water displaced by the rock. And we just need to add these two volumes together. So the volume of water displaced by the boat and the volume of water displaced by the rock, to get the total volume of water displaced in the second scenario. And this is capital M over the density of water plus small m over K density of water. And if here we divide both the numerator and denominator by K, we get that M plus M over K divided by the density of the water is equal to the total volume of water displaced when the rock is outside the boat. And now we just need to compare these two volumes. So which one is bigger? So the volume displaced when the rock is inside is this, and when it's outside is this. So we know that the densities are the same, the capital M's are the same, so basically we just need to compare M and M over K. But we know that K is greater than 1, so when we divide M by K, it's less than just M, therefore M is greater, which means that the volume of water displaced when the rock is inside the boat is greater than the volume when it's outside. But what does it tell us about the level of the water? So to make it simple, let's say that we have two beakers and they have the same amount of water there, and we place two different objects there. So clearly this object displaces more water, so the volume displaced by this object is larger, and therefore the water will go up, the level of water. And this means then if the volume of water displaced is larger, then the level of water is larger. Therefore the height of the water when the rock is inside is greater than the height of the water when it's outside. And by the way, we can also calculate the difference in the volume displaced. So delta V is equal to V inside minus V outside, and this is m plus m minus m over k over the density of water. So we can cross big M's. What we get is m minus m over k over the density of water, which is m times 1 minus 1 over k in the brackets over the density of water. Now we can multiply both the numerator and denominator by k, and what we get is m times k minus 1 over k times the density of water. But we said that k times the density of water is the density of rock. Therefore it is equal to m times k minus 1 over the density of rock. And this m is the mass of the rock. And mass over the density is volume. Therefore m over density is equal to the volume of the rock times k minus 1. So this shows us by how much does the volume of water displaced change. And to find the height, so the difference in height, we just need to know the surface area of the water and divide the volume by the surface area, and we get the height. So delta H is equal to volume of the rock times k minus 1 over the area. And this is only true when k is greater than 1, which means that the density of an object which we throw overboard is greater than the density of water. But what if we threw not a rock, but for example apple or any other object which has a density less or equal to the density of water? So we can also write it as density of A is equal to k times density of water, where k is less or equal to 1. In this case then, small m becomes the mass of an apple, not the rock. And if we look on the first scenario, it doesn't involve any densities of an object which the person holds. It involves only masses. Therefore, the volume of water displaced when an object is inside doesn't change. But it does change when it's outside. Since we treated the boat and an object separately, this means that nothing changes to the boat, because what we only changed is the density of an object, and it's not in this equation, it's here. So we know that any object which has density less than or equal to the water's density will float, and therefore we can use this formula again. So the upthrust is equal to the mass of an object times g, so it's weight. So let's draw an apple here. Yeah, so this is its weight, mg, and this is the upthrust, and it floats. And it's also equal to rho vg, rho of water of course, times volume of water displaced times g. And again we can cross g's, and what we get is the volume displaced by the apple is equal to the mass of an apple over the density of the water. So now we don't consider the rock, we don't have a rock, what we have is only the boat and an apple. And we need to add these two volumes together as we did with the rock. So the total volume when an apple is outside is equal to the volume displaced by the boat plus the volume displaced by an apple. And this is the total mass over the density of the water, which is exactly the same as it was when an apple was inside. Therefore, for an apple, volume displaced when it's inside is equal to the volume when it's outside. And therefore, the level of water or height is exactly the same. So, to summarize everything, we can say that if the density of an object is greater than the density of the water, as it was in case of rock, then what we had that volume when it's inside is greater than the volume when it's outside, volume of water displaced, and therefore the height is greater when it's outside. So we can write it here. So H in is greater than H out. But in case of apple, which had a density less or equal to the density of water, so any object, it can be any object, not on the apple. So the level of water, as we saw here, and obviously the volume of water displaced, is the same whether it's inside or outside the boat. So that's what we get. And an obvious question to ask is, can we get the height of the water when an object is outside higher than when it's inside? Can we get this? And the answer is no, because we considered all the possible values of the density of an object we throw. So it can only be either greater than the density of water or less or equal. These are the only options we have. And if you still don't trust me, then you can just look at the formulae. So the only thing we can change is the density of an object. And when it's inside the boat, the density doesn't affect the volume displaced at all. The only thing which does is the mass. So this means that even if we have a bicycle on the boat or a mountain of popcorn, as long as they have the same mass, the volume of water displaced will be the same. And in this case, if we look at the boat, the volume of water displaced by the boat is not affected by the density of an object we throw, since there is no density of rock or apple. But what is affected is the volume of water displaced by an object. So here, when the density is greater than the density of water, we have that the volume displaced by the rock is equal to the mass over the density of the rock. And if the density is less or equal to the density of water, then the volume of water displaced is given by this formula, which is the mass, the same mass, but divided by the density of water. And we know that this is true when the density of rock is greater than the density of water. Therefore, this value is greater, and when we divide mass by the greater value, we get that the volume displaced by the rock is smaller than the volume displaced by an apple. Which means that the maximum volume which an object can displace is when its density is less or equal to the density of water, because in this case we use this formula. If its density is high, then we use this formula and we get less volume, and we want as much displaced volume as we can to increase h. But this is the maximum we can get. And if we use this and substitute it, so if we add this to the volume displaced by the boat, we get exactly the same as what we've started with. Therefore, the maximum height we can get when an object is outside can't be greater than the height when it's inside. So this is the maximum what we can get. So this can't be true. But you may say, what if that guy in the boat is so irrepressible that when an object floats, he decides to push it further into the water? How dare is he? So can he increase the height then? And the answer is no again, because when he does it, he pushes the ball down with the force F, but due to the reaction force, the ball pushes his hands with the same force F, and we have the same weight, the upthrust force and weight of the ball and its upthrust force as well. So many forces in this case. So if we take the upthrust force which acts on the boat, it is equal to the weight minus F, because F acts in the same direction as the upthrust force, and the upthrust force on the ball or apple is equal to its weight plus force F, because the weight and force F from that human is in the same direction. And if we add these two forces, so to calculate the total upthrust force, what we get is mg plus mg, which is m capital plus m small g, and this is exactly the same as we had in the beginning. So therefore, the total upthrust force when it's outside, when apple is outside, is exactly the same when it's inside. So what we get is out is equal to in, and this means that the volume of water displaced is the same again. So this guy didn't achieve anything by pushing the ball even harder. Okay, but what if this guy has a friend which stands on the coast? So this is his friend, this is coast, and this is the initial guy in the water and an apple floating, and his friend uses a huge stick to push the ball with force F again. So therefore there is a reaction force F upwards, and again weight, upthrust on the ball, and weight of the ball. But in this case, the upthrust on the boat is equal to mg, since this person doesn't push the apple, and the upthrust on the apple is equal to mg plus F due to this force. And if we add those together, we get that the total upthrust force is equal to m plus m times g and plus F, which is greater than the initial upthrust by F. So this is greater by initial F upthrust. Therefore out is greater than in, and this is exactly what we wanted to get. But we said that it's not true. How come? But this is not true only in closed system. So this is the closed system and no external forces can intervene. And this is the external force clearly. This guy is outside the system. He's not even in the water. So the point is that unless you have a friend on the coast with a huge stick or any other external force acting on one of the objects, then when you throw any object outside the boat, don't expect for the water level to rise. It will not rise. It will either stay the same if the density of an object you throw is less or equal to the density of water, or it will drop. So this is it. Thank you for watching this video. Leave a like if you enjoyed it and share it with your friends or teachers, and leave a comment so I could know what did you like and what you didn't and what can I improve. See you soon.